in the presentation for Team 15 along with Rohan Misra. So going into our project, so with basketball being such a popular pastime in the US and fans spending so much time not only watching the sport but also on other activities around it such as betting, the team wanted to explore the applications of machine learning as it relates to betting during the NBA season. So similar projects to this have been done in the past using models such as logistic regression, neural networks, and random forests. And specifically in our iteration, we decided to use a data set that consists of data from the regular and postseason NBA games from the 2007-2008 to 2021-2020-22 seasons. And for each game, the data set includes several attributes that detail statistics for each of the teams playing, in addition to some betting data. So one of the most popular types of betting relates to binary outcome, meaning whether a team wins or loses, and this is what we decided to focus on. In addition, we wanted to broaden the scope of this to also look into distinctions between postseason and regular season games to see if there's a distinction in predictions between the two. So using this data that I described, the team wanted to test 3 different models, as well as experiment with PCA in order to see if dimensionality reduction is necessary. So going into some of the pre-processing that we did for this, we first started by adding some fields. The first of these is a playoff indicator, which denotes whether a game occurred during the postseason or the regular season. We also encoded a team name categorical variable. And then lastly, we created this distinction in the naming between the attributes that were related to the home team and the away team. After this, we decided to standardize the data, which would be very helpful in conducting PCA. And then lastly, we dropped some columns that we deemed to be unnecessary, such as the date and index. And then we also dropped columns that would help the model kind of cheat in its predictions of outcomes, such as a score feature and some of the betting data. So after this, we decided to begin our PCA analysis, and we used a 95% threshold for variance, and we found that this threshold was reached at 39 features. So at this point, we have 2 data sets, one that has PCA conducted on it, and the second, which is one without PCA. And we wanted to run both of these data sets through each of the 3 models in order to compare for results. So the first model that we decided to use was a feed-forward neural net, and we use this because it's commonly used in regression and classification. We decided to tune some of the parameters to test for optimality, and we decided that 4 layers was optimal with 2 inner layers, 1 input and 1 output layer. We also decided to use dropout to prevent overfitting. For our activation functions, we decided to use ReLU, or rectified linear unit, for the inner layers, largely for its efficiency. And then for our outer layer, we used a sigmoid function, which is standard for binary classification. And we did this for each of the data sets, both the PCA and the non-PCA. Going into some of the actual results from a model, we found that using an atom optimizer and an MSE loss function as a mean for updating weights and the loss function, we saw that loss was minimal in both cases of the model. Beyond this, we wanted to look at the confusion matrix themselves. So we found that specifically the model without PCA, the home losses, as we see through the 1602 and 594, were very accurately predicted, as well as the home wins were very accurately predicted, as well as the home losses. Looking at the model with PCA, we see that the home wins were also very accurately predicted. However, the home losses were a lot less accurately predicted in this instance. However, both models performed relatively well, with the area under the curve being very close to 1 of this graph. And then lastly, looking at the F1 and the accuracy, these were relatively negligible as it relates to both of these models.
After running the feed-forward neural network, we then look to the random forest algorithm. In testing this model, we evaluate 4 different values for the hyperparameter of decision trees: 10, 50, 100, and 150. After comparing the trade-off between model accuracy and training time, we finally decided to use 100 decision trees. This is seen in our model results. Looking to metrics such as the accuracy and F1 scores, we see them fall into the range of 0.66 and 0.72 respectively, which is aligned with the findings from the neural network. Furthermore, we look at the confusion matrix for the non-PCA run, and we see again that the model accurately predicts home team wins, but is significantly less adept at predicting home team losses. Introducing the PCA iteration, we see similar thresholds for accuracy, F1 scores, and other performance metrics. However, the increased type 2 error shown in the non-PCA model is exaggerated, as the model actually more frequently incorrectly predicts a home team loss versus correctly predicting a home team loss. Here we see the visualization of the values of the hyperparameters, seeing that as we increase the number of decision trees, the model F1 score improves, and we select one that balances this trade-off. Here we see a visualization of the accuracy and F1 scores of the PCA and non-PCA iterations respectively, again validating that they fall into similar thresholds. Finally, we run a logistic regression on both PCA and non-PCA datasets. It's interesting to note that for the non-PCA model to achieve convergence, we had to increase the number of model iterations. Again, we look at performance metrics and see that they're largely aligned with the first two runs of the model, with the F1 score being 0.73 and accuracy being 0.67 for the non-PCA run. Again, we see that the model is adept at predicting home team wins and actually behaves as a random classifier when predicting home team losses, as there's no clear trend. Once more, we see that performance metrics are generally similar. However, the confusion matrix shows that the effect of increased type 2 error is exaggerated for the PCA run. However, type 1 error decreases. Finally, we see a comparison of accuracy across both the PCA and non-PCA runs, again validating that models perform generally similarly. Contextualizing results, we see that PCA generally has little to no improvement on model output. This is because much of our explained variance is spread out across each of the 100 or so fields, and that looking at a linear combination of 39 of them does not necessarily improve model performance. This is the case for all models. It's important to note, however, that the non-PCA neural network run had the highest predictive capability both for home team wins and home team losses. This leads us to suggest this algorithm for a team-agnostic bettor that wants to maximize results regardless of setting. However, a fan who typically bets for their home team to win might be interested in the PCA including neural network run, as that maximized the home team win capability at the expense of an increased type 2 error. Again, looking at model comparison, we see that F1 score, accuracy, ROC, AUC curve values, and mean squared error are generally similar across all of our models. And this accuracy threshold suggests that our model is adept at predicting wins, however, is slightly subpar relative to the gold standard in the industry. And looking forward, we see opportunities to increase this by further weighting the value of home team advantage. The type 1 and type 2 errors of our model suggest that we may be incorrectly or overweighting the value of a home team game taking place, as well as potentially incorporating momentum, such as the inclusion of a streak variable, as well as potentially factoring player attributes to our data set. Including these metrics or these predictors would help us in our goal of predicting playoff matchups, as these factors are generally perceived to be more important in a playoff setting. Including these variables, we hope to match our model prediction with that of the gold standard in industry.